everyone, and welcome to the second chapter of our Chemistry O-Level Lessons series. This chapter is called Particles of Matter, and here we have the learning objectives of this chapter. The topics of this chapter would be given in the description below, along with their timings and chapters. So, in this chapter, we are going to learn to describe the solid, liquid, and gaseous states of matter. We are going to describe and explain the evidence for the movement of particles in liquids and gases. We're going to learn to explain everyday effects of diffusion in terms of particles, for example, spread of perfumes. How we can state qualitatively the effect of molecular mass and temperature on the rate of diffusion. We're going to explain the interconversion between these three states in terms of the kinetic particle theory. And we're going to explain the energy changes involved in the changes of state. So these are some of the learning objectives of this chapter. So now without further ado, let's dive into this chapter. Starting with states of matter: solid, liquid, and gas. So, matter is any substance or material that occupies space and has mass. And so, this will include buildings, soil, plants, and animals, as well as invisible substances such as air, because they also occupy space and have mass. So, matter can exist as a solid, liquid, or a gas. These are called the three states of matter. So, let's look at these three states of matter in more detail. Here we have a solid, a liquid, and a gas. So, the properties of each of these. Solids have definite shapes, whereas liquids take the shape of their container. They do not have their own specific shape, they take the shape of their container. Gases also take the shape of their container. Secondly, solids have a fixed volume. Liquids also have a fixed volume. But gases, on the other hand, take on the volume of their container, because gases are easily compressible. Here we come to the third property. Gases are easily compressible, whereas liquids are difficult to compress. And solids are not compressible at all. So solids normally have a high density, liquids have a medium density, and gases have a very low density. That's why they're so light, Lastly, solids do not flow. Liquids and gases both flow, because a solid has its own fixed volume and a definite shape, so it remains like that. It doesn't flow. Okay? So these are some things that you probably would have known already before, but here you can see the differences between these three states of matter. So solids normally have a greater mass than liquids or gases, as they are often hard and dense. They have a high density, we read before, and they therefore have definite shapes and fixed volumes, because they have a greater mass than liquids or gases. Liquids have a medium density and gases have a very low density, which suggests that the particles per unit volume in liquids or gases are much less than solids. Solids have more particles per unit volume, more molecules per unit volume. That is why they're dense, and that is why they're hard as well. That would suggest that they have a greater mass than liquids or gases, and that is also why they have definite shapes and fixed volumes. Liquids, on the other hand, are not hard. You can push your finger through a liquid, and as a result, they do not have a fixed shape either, but take on the shape of their container that they are in. Liquids, however, do have fixed volumes, so if you pour a liquid from one container to another, its volume remains the same. So, the difference between liquids and solids is that solids have their own shape and fixed volumes, but liquids take on the shape of their container and have a medium density, something like that. So that is why they're softer than solids and they flow. They have a flowing consistency, whereas solids have definite shapes. But liquids do have fixed volumes. They might not have definite shapes, but they have fixed volumes. Then we have gases. These are normally very light in comparison to solids or liquids. They have low densities, that's the reason why. And they do not have fixed shapes or volumes at all. They do not have a definite shape or a volume even. A gas will always take up the volume of its container. Why do we say that it doesn't have a fixed volume? Because gases are compressible. The molecules of gases are widely spaced apart. So it is easier to compress them because there is space in the molecules. So they can be compressed. You can see this over here. The solid molecules are very closely together. Liquids are spaced but not that much as a gas is. Gas molecules are widely spaced, and so they are easy to compress compared to a liquid or solid. Liquids are also compressible, but they are difficult to compress. Gases are easily compressible because of their molecular arrangement. Solids are not compressible. They do not have the space to be compressed. Okay? So, now that we've understood the properties of the three states of matter, solid, liquid, and gas, we can move ahead on to understanding the changes of state. So, for example, we can convert solids into liquids by heating, and further heating can change a liquid into a gas. So, these are the changes of the three states of matter: from solid to liquid, from liquid to a gas, from a gas to a solid, from a gas to a liquid, from a liquid to a solid as well. So, these are some things to remember here. Number 1, the constant temperature at which pure solid changes into a liquid is called its melting point. This is also written as m.p. MP, melting point. So, the temperature at which a pure solid changes into a liquid is called its melting point. And this temperature should be constant. This depends on the material, the temperature. Not all the solids have same melting points. Each material, each element has its own melting point. For example, we have ice. The melting point of ice would vary if the ice is not pure. But if it is a pure solid, then the temperature at which it would melt would remain constant. We're going to look at this in much detail afterwards. The second thing that we also have to remember is that the constant temperature at which pure liquid changes into a gas is called its boiling point. You know, we boil the water to cook food. That is the boiling point of water. There is a boiling point of water when it starts to boil. This is also written as B.P. BP. Boiling points are also at constant temperatures. And remember, at which pure liquid changes. A liquid should be pure in order for it to have a constant temperature at which it boils. And when it boils, the liquid changes into a gas. So, these are the changes of state. The melting point at which the solid changes into a liquid, and the boiling point at which a liquid changes into a gas. Okay? So, when a solid changes into a liquid, it is said to melt. The ice is melting. The chocolate is melting, you know. We've heard these things before. So, when a solid changes into a liquid, it is said to melt. And when this liquid cools into a solid, it is said to freeze. So, for a pure substance, the temperature at which these changes take place is exactly the same and occurs at the melting point of the substance. So, liquids can change into a gas without boiling. And this is when a liquid evaporates. Here, the liquid becomes a vapor at a temperature below the boiling point of the liquid. So, evaporation occurs below the boiling point of the liquid. The liquid starts to become a vapor at a temperature below the boiling point. So, when a puddle evaporates, the water particles evaporate from its surface into the air. So, the particles change from a liquid into a gas, but without boiling. That is called evaporation. So, evaporation is a much slower process than boiling and occurs only at the surface of the liquid. So, the molecules at the surface of the liquid start to move apart because they have a lot of kinetic energy and very vigorously start to push each other, move apart away from each other, and in the end, they'll leave the surface of the liquid and turn into a gas. So that is what evaporation is. So, melting points and boiling points are important in identifying a substance and testing its purity. So, pure substances have definite melting and boiling points. As we read over here, the constant temperature at which pure solid changes into a liquid is called the melting point, and the constant temperature at which pure liquid changes into a gas is its boiling point. So, only a pure solid will have a constant temperature, will have a constant melting point. If the solid is not pure, the melting point would vary. But if it is pure, like if the ice is pure, then it would always have a same melting point, the constant temperature for the melting of the solid. In the same way, if the liquid is pure, it doesn't have anything mixed within it, or it's just pure liquid H2O, then the boiling point would always remain the same. So, the presence of an impurity will cause boiling points to rise and melting points to fall. Boiling points to rise and melting points to fall. You should remember this. So, here we have the different melting and boiling points of different materials. These are the melting and boiling points of pure materials, pure substances. Here we have water. The melting point of water is 0 degrees centigrade and the boiling point is 100. Now, if the water is not pure, it's not only water, it's mixed with something else, for example salt, then the boiling point would rise and the melting point would fall. So, pure water has a boiling point of 100 degrees centigrade. Nitrogen gas has a melting point of minus 210 degrees centigrade and a boiling point of minus 196 degrees centigrade. Oxygen gas has a melting point of minus 218 degrees centigrade and boiling point of 183 degrees centigrade. Carbon dioxide gas has a melting point and the boiling point same. These are minus 78. Alcohol, also known as ethanol, has a melting point of minus 117 degrees centigrade and a boiling point of 78 degrees centigrade. Salt, also sodium chloride, has a melting point of 801 and a boiling point of 1467 degrees centigrade. Copper has a melting point of 1083 and a boiling point of 2595 degrees centigrade. Iron has a melting point of 1535 degrees centigrade and a boiling point of 3000 degrees centigrade. Carbon has a melting point of 3550 degrees centigrade and the boiling point of 4827 degrees centigrade. Okay, so these were the melting and boiling points of these common substances. Now, some substances do not exist in the liquid state at ordinary pressures but change directly from solid into a gas. So, this is called sublimation. So, examples of substances which sublime are solid carbon dioxide, ammonium salts, and iodine. So, in the previous table, you might have thought why carbon dioxide has the same melting and boiling points, minus 78 degrees centigrade. Carbon dioxide gas melts at this temperature as well as boils at this temperature. The reason is because carbon dioxide sublimes, so it can change directly from a solid into a gas. So what happens is that when carbon dioxide reaches its melting point, the solid changes into a liquid, but as it changes into a liquid, it starts to change into a gas at the same time because the boiling point is also the same as the melting point of carbon dioxide. So the substances that sublime, they are solids. When they change from a solid into a gas, there is a tiny fraction of a second where they turn into a liquid as well. Only then they will be able to turn into a gas. So the solid carbon dioxide changes into a liquid for a very short time at its melting point, and then the liquid changes into a gas at the boiling point, which is the same as the melting point. And so usually we are not able to see this change from solid to a liquid. We only see the change of solid into a gas. And so that is why we call this sublimation. It seems as if the solid changes directly into a gas, even though there is a transient moment where the solid changes into a liquid as well. So this is what sublimation is. Now we're going to investigate the changes between the states of matter. To do this, we can plot a heating or cooling curve. In these, the temperature and time are recorded at regular intervals on a graph. This axis represents temperature and this axis represents time. So as time goes on, the heat is added. This is a heating curve. In a cooling curve, as the time increases, the heat is removed, so the temperature comes down. As you can see, the cooling curve has the same shape as the heating curve, except that it goes in the opposite direction. Now, the flat sections in each of these graphs indicate a change of state. Let's look at the heating curve first. We're going to take water as an example for this. So first, the water is a solid, ice. When the temperature reaches to 0 degrees centigrade, it starts melting. But during melting, the temperature remains constant. It doesn't increase. It doesn't go more than 0 degrees centigrade because it will melt only at 0 degrees centigrade. So while it is melting, the temperature remains constant at 0 degrees centigrade. So when the solid changes completely into a liquid, the temperature rises till it reaches to 100 degrees centigrade and the liquid starts to boil. And that is where vaporization occurs. So this is where the liquid turns into a gas at 100 degrees centigrade. Again, there's a flat section because the temperature remains constant during the change of state. So this is the heating curve of water. Then we have the cooling curve. In this cooling curve, the gas, which is the steam, comes to 100 degrees centigrade and condenses into a liquid. There is a flat section again because there is a change of state. So when there is a change of state, the temperature remains constant. At 100 degrees centigrade, the gas changes into a liquid again. And this is a cooling curve. So the heat is being removed slowly. Then after turning it into a liquid, the temperature falls down to 0 degrees centigrade where the liquid starts to freeze. So at 0 degrees centigrade, the liquid turns into a solid. So the lower flat section, these are the changes from solid to liquid and occurs at the temperature of the melting point. So whether it's water or any other substance, these sections would indicate the change from a solid to a liquid or a liquid to a solid. In this case, it's liquid to a solid. In this case, it is a solid to a liquid. And the higher flat section, this one, is the change from liquid to a gas and occurs at the temperature of its boiling point. So in each of these flat sections, the temperature remains the same over a period of time as the heat energy is being used to change the structure of the state. Like I said, during this change of state, the temperature remains constant. So when a solid changes into a liquid, during this change of state, the temperature would remain 0 degrees centigrade. And when a liquid changes to a gas, during this state of change, the temperature would also remain constant, which is 100 degrees centigrade. So this is what the cooling and the heating curves are. These are to show that during changes of state, the temperature remains constant, whether it is melting, vaporization, condensation, or freezing. So there are 6 changes of state. Here we can see this. From a solid into a gas, and from a gas to a solid. When a solid changes into a gas, it is sublimation. And when a gas changes into a solid, it is deposition. When a solid changes into a liquid, it is melting, and when a liquid changes into a solid, it is freezing. Then we have liquid to gas and gas to liquid. When a liquid changes into a gas, it is evaporation, and when a gas changes into a liquid, it is condensation. So this is the changes of state. Now we're going to move ahead onto the evidence of particles. How do we know that all matter is made up of particles? So we're going to look at the evidence of particles now. So all matter is made up of particles with spaces in between. And evidence for the existence of such particles comes from many different sources. The first source we're going to look at are crystals. So the existence of substances in crystalline form can only be explained if we assume that matter is made up of particles. Here you can see crystals. Crystals grow as layers of these particles build up on the crystal surface. And the end result is that particles arrange themselves into regular rows and give the crystal its regular shape, with flat surfaces and straight edges. So, this is one evidence of particles because the existence of these crystals can only be explained if we assume that matter is made up of particles. The particles arrange themselves into regular rows like these. This is one particle, here we have many more particles, and in the end, we have a crystal with flat surfaces and straight edges. So this is one evidence of particles. Then we have diffusion as another evidence of particles. Diffusion is basically the natural mixing of particles. If you leave some reddish-brown bromine gas in a test tube with another test tube of air above the gas, you will find that the red color of bromine gas will soon spread to the test tube on the top. So this is diffusion. The simple definition of diffusion is that it is the net movement of particles from a higher concentration to a lower concentration. So if food is cooking in the kitchen and you are sitting in your room above, the food molecules would reach your nose and you would be able to smell the food. So that is diffusion. Food molecules diffuse from the kitchen, and that is a higher concentration of those molecules to a lower concentration where there are less molecules. In the same way, the reddish bromine gas in the test tube mixes with the air because of this concentration gradient. So diffusion is the net movement of particles from a higher concentration to a lower concentration. And diffusion can only take place if matter is made up of particles. If matter had been continuous, there would not have been enough space for gases, liquids, and solids to mix together. In fact, the rate of diffusion is inversely related to the mass of the particles. Therefore, a dense gas like carbon dioxide with heavy molecules diffuse more slowly than a light gas like hydrogen. Okay, so the rate of diffusion is inversely related to the mass. This means that if the mass increases, the rate of diffusion decreases, and if the mass decreases, the rate of diffusion increases. So this is what inversely related means. So diffusion is another evidence of particles because it can only take place if matter is made up of particles. Only then there would be a concentration gradient, and only then the molecules would be able to move. So here we have some more evidence of particles. For example, sugar dissolves and disappears in the coffee because its particles become spread out through the coffee. So why does sugar dissolve and disappear in the coffee and we can taste it? This is because the sugar is made up of particles, and these particles become spread out throughout the coffee. The second example is perfume. Perfume travels as its particles are in continuum motion and move through the spaces between the air particles. This would be an example of diffusion as well. Lastly, when metals are heated, they can fuse together as their particles move and mix together. So when we heat them, due to this high temperature, the particles gain kinetic energy and start moving vigorously, and they move and mix together. So that is when they fuse together. So this is another example and evidence for particles. So speaking of kinetic energy, let's move ahead on to understanding the kinetic theory of particles. Particles on the move. So this is a theory about the way particles move about in solids, liquids, and gases. By particles we may mean molecules or atoms. The word kinetic comes from a Greek word for moving. Like I gave the examples of when metals are heated, they gain kinetic energy and move and mix together, so they fuse together. Now, solids have a definite shape and are not easily squashed or stretched. Accordingly, their particles are packed closely together with strong attractive forces between them. So there is little movement of these particles except to vibrate about fixed positions. That is why solids are difficult to be squashed or stretched, because they have strong attractive forces between their particles, and there is little movement of these particles except to vibrate about fixed positions. But liquids, on the other hand, take the shape of whatever container they are kept in. So they do not have a definite shape, and they are only slightly compressible. Solids are not at all compressible. Liquids are only slightly compressible, and the attraction between the particles of liquids is weaker than in solids because of the greater distances between the particles. So particles are further away from each other than the solid particles are. In a solid, the particles are closely packed together with strong attractive forces between them. But in liquids, the attractive forces is weaker, as you can see here in this diagram. The solid particles are closely packed together, whereas the liquid particles are further away. And the gas particles are even more away from each other. So gases take up whatever space is available to them. This is due to diffusion. So gases are compressible because the particles of a gas are spaced well apart. Hence, the attractive forces between the particles are also very weak. So, the kinetic theory takes these models of state and explains the interconversion between them. It says that when a solid is heated to its melting point, it melts, as the particles have gained more energy and move about more. So when they move about more, they become more widely spaced. After colliding with each other, they become widely spaced and therefore become a liquid. Like this. As you can see, this ice cube is melting. When it reaches 0 degrees centigrade, it melts and becomes a liquid. If more heat energy is supplied, the liquid changes at its boiling point into a gas, into a vapor. At this temperature, the particles of a liquid have gained sufficient energy to escape from the surface of the liquid. They then become sufficiently active and far apart to be called a gas. This is evaporation, what happens during boiling. So, the liquid in this cup is turning into gas. So, let's look at the particles of solids, liquids, and gases one by one. Solid. We're taking ice as an example. So the particles in a solid are, number 1, very close together, as you can see here. Number 2, arranged in regular rows, as also what you can see here. Number 3, held together very tightly. Number 4, not moving from their positions. And number 5, vibrating about fixed positions. Because they do not have any space to move about, they only vibrate about fixed positions. So this is solid. Then we have liquid. The particles in a liquid are further apart, as you can see here. And number 2, they are not regularly arranged. 3, they are not tightly held. 4, they are moving about because they have space to. 5, they change places. Whereas solid vibrates about fixed positions, in liquid, particles change places. Then we have gas. Steam as an example. The particles in a gas are furthest apart. They are randomly arranged, they are free to move, they are moving very fast, and they move in all directions. They have a lot of space, that's the reason why. So, this was it for today's chapter. Particles of matter. In this chapter, we've learned to describe the solid, liquid, and gaseous states of matter, how we can describe and explain the evidence for the movement of particles in liquids and gases. All the learning objectives that we read in the beginning of the chapter, we have completed them. In this chapter, we read about solids, liquids, and gas, the states of matter, the changes of the states of matter. In this, we learned about the melting point and the boiling points, the different processes like evaporation, condensation, freezing, melting, deposition, and sublimation. We saw different substances and their melting and boiling points. We learned about the cooling and heating curve. Then we saw the evidence of particles, including crystals and diffusion. Then we saw the kinetic theory of particles on the move. And lastly, we saw the arrangement of the particles of solids, liquids, and gases. So this was it for today's chapter. I hope you've understood everything. We completed the second chapter of our Chemistry O-Level lesson series successfully. And the next chapter is going to be methods of purification. So thanks for watching, and I'll see you in the next video.